This conference will now be recorded.
Hello everyone. Today we will discuss only problems. Here the first problem, and topic will be covering the whole chapter. Assertion reason type of problem. Vinyl halides do not undergo nucleophilic substitution easily. Now vinyl halide means this type of structure. CC double bond, and with this directly the halogen is attached. In the first statement it is saying that this type of halides there is no nucleophilic substitution possible easily. And in reason, the statement given, even though the intermediate carbocation is stabilized by loosely held pi electrons, the cleavage is difficult because of strong bonding. So another statement is given in reason, and 4 different options are there. The first option is both the statements will be incorrect. Then both A and R, both are fine, correct, but R is correct explanation of A. And in the second case, again both are correct, but R is not correct explanation. And in case of 4, the first statement is correct, but the second statement is not correct. Now, this is the structure of vinyl halides, and when it is vinyl halides, this type of resonance is possible. So here we have taken very simple, that is the simplest structure of vinyl halide that is possible, CH2 double bond CHCl. Here we have taken chloride. You can also take another halogen. And what kind of resonance is going on? The lone pair which is present over the halogen. I can also show the same with the general structure like this. Now there will be negative charge in this carbon, and the second carbon double bond, then halogen which is positively charged. So this is the resonance that is possible. Now because of this type of resonance, here double bond character is generated between carbon and the halogen. So because of this partial double bond character of carbon halogen bond, halogen when it will be leaving, that is the cleavage of carbon halogen bond, that is actually very difficult process. That is cleavage of this bond or this bond, it is very difficult process, even that is if the reaction is occurring. So this is the actual reason for which it is not undergoing nucleophilic substitution easily. So the first statement is obviously correct. Now the first statement, it is simply saying that there is no nucleophilic substitution occurring easily in case of vinyl halides, but there is nothing about the reason. So the statement is correct, but what is the reason? The reason is because of this partial double bond character. Now in the second statement, that is the reason statement, is this particular reason is mentioned or not, that we have to see, because if there is some other reason mentioned, then obviously it will not be correct. Now it is saying that even though the intermediate carbocation is stabilized by loosely held pi electrons. Now intermediate carbocation means if you are considering the cleavage of this CX bond, then there will be positive charge over this sp2 hybridized carbon. Now in this carbocation, there is actually no stabilization, but the statement in reason, it is saying that it is stabilized by loosely held pi electrons. Though it is true that there is pi electrons, but this positive charge is not stabilized by the loosely held pi electrons. But why it is so? So look at this structure. Again the same molecule is taken, which is vinyl chloride, and after resonance, after the cleavage of this carbon chlorine bond, there will be positive charge CH2 double bond CH. Now here this positive charge, as it is present over this carbon, that means there will be a vacant pi orbital. Okay, so suppose here the orbital that I am coloring, it is the vacant one, right? And the other pi orbital that is also shown here, that I am drawing with blue color. So this pi bond that is already present in the molecule, that is this pi bond. This is sigma, this is pi. So the first pi bond which is already present in the molecule, and this is the vacant p orbital. Now this orbital and this one, they are 90° to each other. And as they are 90° to each other, so obviously stabilization is not possible, because for stabilization they must be in the same plane. That is why intermediate carbocation is not stabilized by loosely held pi electrons, because the empty orbital, that is a vacant orbital, it is at 90°, so cannot overlap with the p orbitals of the pi. And that is why the reason that is given, it is not correct. Now suppose if the positive charge is present in allylic type of structure, that is CC double bond, then there is positive charge. Now in this case, the p orbital, that will be in the same plane with the p orbital of the already present double bond. So in this case, stabilization is possible. We also know that in allylic carbocation, this type of resonance is possible. So the new structure that you are getting, now positive charge here. So because of this type of resonance, here stabilization is possible. But when it is vinyl, that is positive charge is present over doubly bonded carbon, now it is not possible because of this reason. So here statement given in assertion, that is correct. A is correct statement, but R is not correct. So option 4 will be the correct option. This is multiple correct choice, so more than one option may be correct. In which of the following cases rate is dependent upon concentration of nucleophile? Now, if we look at the reactions carefully, first you have to understand what kind of reaction it is. Is it substitution, elimination, or addition? So first you have to understand the type. So in option A, there is a chlorine attached to this carbon, but it is not directly attached to aromatic carbon, so you can consider it as if it is haloalkane. In presence of fluoride ion, there is product formation. Now, actual structure of the product is not given, but here it is mentioned that specific rotation is 0. That means there will be decimization. Then the second option, here we are using sodium iodide and acetone. Now acetone, remember, it is polar aprotic solvent, and this type of solvent normally used in SN2 reaction. So sometimes from solvent nature also you can have some idea about the type of the reaction. And iodine is attached to aliphatic, so this is also haloalkane. And here actual reagent is I minus, which will attack at this carbon, and CI bond will be broken. So nucleophile is I minus. The next reaction, which is option C, here we have aromatic ring. Chlorine is directly attached to aromatic ring, so we can consider it as if it is haloarene. We are using NaOH, but actual nucleophile is HO minus. And the last one, again it is haloalkane because there is no aromatic ring. Sorry, here chlorine is attached to this carbon, but it is not directly attached to pH. So you cannot say it is haloarene. This is actually example of haloalkane. Here also we are using AgI, that means I minus is the actual product, and there is product is mixture of stereoisomer. That means there will be both R isomer as well as S isomer. That is, the product is chiral. Now all these reactions, though product structure is not given, one common point you can find that they are either haloalkane or haloarene, and there is some presence of nucleophiles. So obviously all these reactions will be substitution type of reaction. Okay. Now in substitution we know there are two types of mechanism. It may be SN1 or it may be SN2. In case of SN1, which is two steps reaction, from the rate expression you can understand, which is basically, suppose rate is smaller, so rate is equal to rate constant into alkyl halide Rx. But there is no concentration term mentioned for the nucleophile. But when it is SN2, now it is not only the concentration of Rx, that is the starting alkyl halide substrate, but there is also the concentration of nucleophile. So this is for SN2. The second one is for SN2. So that means you can also say that this question is as if it is asking in which of the following cases rate is following the rate of, that is SN2 mechanism, because only in SN2 mechanism concentration of nucleophile rate is dependent on the concentration of nucleophile. Fine. Now in the first reaction, here chlorine is attached to this carbon, which is benzylic in nature. Now in this case, specific rotation is 0, and here if after cleavage of CCl positive charge is generated on this carbon, that will be very stable. Why? Because with this carbon 2 phenyl ring attached, see, and also there is methyl. So this type of carbocation is very stable. So you can expect SN1 type of mechanism, and specific rotation is also 0. That means when it is SN1 mechanism, basically decimization occurs. So specific rotation will be 0. That is the rotation from the one isomer, which is suppose R, and the rotation that you are getting from S, as both are obtained in 50%, 50%. So obviously it will nullify each other. Ultimately specific rotation will be 0. So the first option, as it is following SN1, so it will not be dependent on the concentration of nucleophile. Now the second one, here two things you may find contradictory, because for polar aprotic solvent, as it is mentioned acetone, now acetone is used in SN2, so it means the mechanism should be SN2, and this alkyl halide that is given, this is also secondary, because the carbon with which leaving group is attached, that carbon is also attached to 2 more carbon. So that is why this is C6H13. Don't think this is pH ring. This is not pH ring. This is a long chain, long alkyl chain. And for 2-degree alkyl halide, SN1, SN2 both are possible. And from solvent acetone, it seems as if it is SN2. But specific rotation is mentioned, it is 0. But you have to remember that here this carbon is carried, right? And after Ci bond cleavage, another Ci bond will be formed. Now, if the initial starting material, that is the molecule that is given in option B, whether it is purely chiral or not, that is whether it is purely S or purely R, that you do not know. That is not clearly mentioned. So that is why, though it is true that in SN2 inversion occurs, that is if you have started from R isomer, you will be ending with S isomer. But if starting material, if it is not 100% R or S, then inversion also we cannot say whether it will occur or not. So that is why this information we have to neglect here. And as it is acetone is there and 2-degree alkyl halide, so you can consider it as SN2. That means here concentration of nucleophile, that is important. Rate will be dependent on that. So option B will be correct. And also one thing, in option A, C, D, there is a single-headed arrow. But see, here we have equilibrium sign. And when there is equilibrium sign, that means according to Le-Chatelier principle, if you are increasing the concentration of nucleophile, okay, then what will happen? Suppose this is the substrate Rx. Nucleophile, you are getting RNA. Now, if you are increasing the concentration of nucleophile, and if the system, it is already in equilibrium. So according to Le-Chatelier principle, the system will be moving towards right hand side, so that more nucleophile is consumed. That means product will be produced in higher amount. So when nucleophile that is concentration of nucleophile is increased, product formation will also be increased, because equilibrium will be shifted from left hand side to right hand side. That means rate is dependent on the concentration of nucleophile. So this is another point of view from which you can understand that option B will be essential. Okay. Now come to option C. In case of option C, now it is haloarene, and for haloarene, if you consider substitution, that is completely different from the mechanism, substitution mechanism that you see in case of haloalkane. So that is why here we know that nucleophilic substitution in case of haloarene, it is possible only when there is strong electron withdrawing group present at ortho and meta. And you can also see that NO2 group, which is very strong electron withdrawing group, that is present in ortho and meta, ortho and para. So that is why this reaction, it is example of aromatic nucleophilic substitution. And what happens actually in aromatic nucleophilic substitution, That is whether it is dependent on the concentration of nucleophile or not. We'll come to that point, but just go to the last one. Here chlorine is basically attached to this carbon, and the carbon with which chlorine is attached, that is attached to 3 more carbon. See, and also it is at the benzylic carbon. That is, it is chlorine, it is attached to carbon which is attached to pH. That means it is benzylic carbon. And for benzylic carbon, SN1 mechanism is highly facile. So that is why here SN1 mechanism will be there. And also mention mixture of stereoisomer. That means both R and S will be there. Though exact ratio is not given, whether it is 80-20 or 90-10, 50-50, nothing is given. Simply mention mixture of stereoisomer. That means both S and R will be there. So this is also not, rate is not dependent on concentration of nucleophile. So B is correct. B will be the correct. But is C is correct or not? We will see that. Yes, this is also. But why it is so? So let's summarize all the points. A, we have already seen, this is SN1. In case of B, it is not only that is from acetone, as it is mentioned, you can understand that it will be SN2, but also as there is reversible sign, that is another indication that reaction will be in the forward direction when you are increasing the concentration of nucleophile. In case of third option, that is C, as it is the example of aromatic nucleophilic substitution, which is also written as in short notation is SNAR. That means substitution nucleophilic aromatic. So in this mechanism also, it is dependent on the concentration of nucleophile. So see, here we have taken this molecule, the molecule that is already given in option C. In the first step, what happens, the nucleophile is attacking at this carbon, that is the carbon with which chlorine is attached. Fine. So this is the first step. And in the second step, what is happening? Now chlorine carbon bond is broken. So this is the second step. Now among these two steps, which one is rate determining step? Here the rate determining step is the attack of the aromatic ring by the nucleophile. That means this is rate determining step. Okay, which disrupts aromaticity. And we know that electron withdrawing groups that helps to stabilize this negative charge. Now as here loss of leaving group, it is not in rate determining step, because see, this loss of leaving group, that is actually occurring in the second step, which is first. So as in the first step, both this molecule and nucleophile is involved. That means slow step, there will be concentration of nucleophile mentioned in the rate expression term. So that is the reason here constant rate of the reaction, that is also dependent on the concentration of nucleophile, because the first step where nucleophile is attacking the leaving group containing carbon, that step is slow step or rate determining step. Okay, so in this way we can choose correct option B and C. And for extra information, see here the last line which is given, though it is not related to this question, but you can also this is very good information. You will also see that in SNAR reaction, sometimes fluorine is also used as leaving group. That you will not see in case of haloalkane nucleophilic substitution. You will never see. Always you will see that in SN1, SN2, what you use? Either bromine, chlorine or iodine, but never fluorine. Fine. But in this case, here as the removal of leaving group is not occurring in the rate determining step, so that is why fluorine can often also be used as leaving group because of its high electronegativity. So here instead of chlorine you can also take fluorine, which is not possible in case of haloalkane substitution reaction. So correct option B and C, this is multiple correct choice. The total number of, this is integer type, monohalogenated. Monohalogenated means only one halogen will be there. Organic products in the following, including stereoisomers, that is also mentioned in the bracket. So you have to find monohalogenated products in the following reaction. But in the following reaction, what is the structure of starting material A? That is not given. right? But one information is given in the bracket, that it is the simplest optically active alkene, and this much information is enough so that you can write the structure of A. So even the structure of A is not given directly, this information will help you to draw the structure of A. And the reagent, what type of reagent we are using? First step, we are using hydrogen and nickel and heat. So this type of reagent, when we use, obviously when there is some unsaturation, CC double bond or C triple bond C, it is clearly mentioned alkene. That means CC double bond will be there in A. You are using H2Ni, that means hydrogenation will be there. Double bond will be converted to single bond. And after that, we are also using halogen and heat. That means CH bond, that will be replaced, one of the CH bond that will be replaced by CX. Now there may be different types of carbon hydrogen bond, but first we have to draw the structure of A. So as it is alkene, so CC double bond must be there, right? And here it is optically active also. Now it is also asking in the question that the final product, in the bracket mentioned including stereoisomer, that means the final product, some of the products may also be chiral, because as it is chiral, the question of this one is arising. That means in the final compound, it is saturated, there is no unsaturation, because you have already used metal and hydrogen. There will be no CC bond, no CC triple bond, right? It is saturated, only C single bond carbon, but still there is some isomer, stereoisomer. So it means that there must be some carbon with which 4 different groups are attached. Then only it is possible. Now in this case, simplest optically active alkene, how you will draw it? So CC unit double bond C, this unit must be present, but there should also be some sp3 carbon. So this is the sp3 carbon, with which that is one of the group is CH double bond CH. Another group, just put H, because you have to draw the simplest structure. But another next two bonds, the groups that you will write now, you cannot put H, because two same groups, if you put, it will not be stereo, that is chiral center. So that is why one methyl group you have to put. And in the fourth position, now methyl group you cannot write. At least you have to write methyl. So this is the structure of A. Just this information, that simplest optically active alkene, this much information will help us to write the structure of this. Okay. Next, if you are using H2Ni with this molecule, the structure of A is already there. The same structure as I have drawn in red color in the left hand side. Here you can see the same molecule is there. Now if you are using hydrogen and Ni, the CC double bond will be converted to CH2 single bond CH3. Now you are using halogen and heat. So how many different types of carbon hydrogen bonds are there that you have to find? Because the final product is monohalogenated product. CH bond will be replaced by CX bond. But how many different types of hydrogens are there, that we have to find. So this is one hydrogen which is that is different chemical environment. How many different types of chemical environment actually present, that we have to see. So this is one each. Then there are two ethyl groups. So you can consider any of these ethyl groups. So suppose this is hydrogen number A, this is B, this is C, and this is D. That means total 4 types of carbon hydrogen bonds are there. These two are same group, so that is why if you put another B and C, it is actually same thing, right? Now we will see the structures. Here when you are removing any of these three D hydrogen, you will be getting this product. Suppose this is number 1, okay, D. you are getting it from D. Then if you are breaking this carbon A hydrogen, you are getting the second molecule, which is I'm writing here A. Then the third one, which hydrogen is removed? This B hydrogen. So this is B, and the last one here, which hydrogen is removed? This is C hydrogen. Okay. Now here, how many stereoisomer, that is including stereoisomer, how many different halogenated products will be formed, that we have to see. In the first structure, is it chiral or not? That you have to check. Now, is there any chiral center? No, there is no chiral center. Because if you consider this carbon here, two same groups are present. So this cannot be chiral center. The second molecule also, there is no chiral center. But in the third molecule, there are actually two chiral centers. Because with the first carbon, there is ethyl group, there is methyl group, hydrogen, and right hand side CHX, CH3 group. So all the four groups are different. And also if you consider the second star mark carbon, with this carbon, there is methyl, this large group, X and H. So two chiral center. So according to this rule, 2 to the power n, it will be 2 to the power 2. That means total 4 isomer will be possible. RR, SS, RS and SR. These are the 4 possibilities. And the last molecule, there is only one chiral center. There is no second chiral center. So that means you will be getting 2 molecules here. So how many now you are getting? From the first product, that is if you are removing D hydrogen, the product that you are getting, only 1. The second one, that is also 1. So this is for D, this is for A. For B, total 4 possible. And for C, it is 2. That means total 8 stereoisomer. The first two are not, that is including stereoisomer. So stereoisomer you are getting only from the last two, not from the first. Okay. So your answer will be 8. It is integer type of problem. Two isomers A and B, same molecular formula, obviously same molecular formula because they are isomer, right? C2H4Cl2, 2 carbon, 4 hydrogen, 2. The first isomer reacts with aqueous KOH and it gives C. C is having molecular formula C2H4O, and another isomer B, same reagent if you are using, now this is producing D, but here formula is different. You have to identify the starting isomers A and B, and you are getting C from A and D from B. That two products also you have to recognize. Okay. Now if we look at the starting material formula C2H4Cl2, just if you remove these 2 chlorine and you add hydrogen, what formula you will be getting? C2H4H2, that means it is C2H6. So this is actually ethane derivative, right? That means there is no double bond. It is derivative of some alkane. You have replaced some CH bonds with chlorine. Okay. So C2H6 is H3C CH3. Okay. Now here, if we put remove 2 hydrogen and put 2 chlorine, 2 different possibilities are there. You can put both the chlorine with same carbon, or you can put chlorine in individual carbon. So based on that, you will get 2 structure, A or B. So this information is already given in the question. Both are treated with same reagent, but C you are getting from first, D you are getting from second. Now depending on what type of isomer you have taken, that is both the chlorine attached to same carbon or not, product is different. So for A, here you can see it is geminal halide. Now geminal means same carbon containing both the halogen. And when it is treated with aqueous KOH, it is not alcoholic KOH. Alcoholic KOH means elimination of HCl will be there. but as it is aqueous OH, it will be substitution. So chlorine is now substituted by OH, but this type of geminal alcohol, they are not stable. So what happens here when there is geminal alcohol? H will be removed and also this OH. So it is net removal of H and OH, and there will be generation of C double bond O. So ultimately, one water molecule removed, you are getting acetaldehyde, which is C, CH3CHO. It is C2H4O. And when both the chlorine are not attached to same carbon, now this is vicinal. I am writing in short VIC. So now, as both the OH are not attached to same carbon, this is not sorry for the interruption. So this is not geminal alcohol, and here water molecule will not be removed. So this molecule is basically D. 2 carbon, 6 hydrogen, 2 oxygen. Okay. So finally, the structures of ABCD. A and B we already know. C is CH3CHO, which we are getting from A, and D we are getting from B, which is ethylene glycol. So our question is identify ABCD. So here all these structures are identified. Here a reaction is given, which is aromatic ring, ortho 1 and 4 position. There is NH2 group and CH. So this is actually, you can call it aniline, methyl substituted aniline, or NH2 substituted toluene. We are using reagent NaNO2HCl mixture, very low temperature, 0 to 5. This type of reagent is used for diazotization of NH2 group. That means we are doing diazotization. There will be NH2 group will be converted to N2 plus. Second reagent is Cu2Cl2 and HCl. And if you are treating diazonium ion with this type of reagent, N2 will be replaced by chlorine. That means in A, NH2 is simply replaced by Cl. Okay, 4-methyl chlorobenzene. But this is not end of the reaction. Next, we are using chlorine and HNu. It is light induced. We are not using any catalyst or metal catalyst, but light is HNu. We are getting B, and finally sodium and diethyl. Major product C that you have to find from the options. Now sodium and diethyl, this type of this reagent, it is specific for a particular name reaction. Try to remember that. So we will move ahead one by one. We have to find the structure of C. So as it is diazonium ion formation reagent, in presence of NaNO2HCl, there is actually formation of HNO2. Temperature must be kept at a very low temperature, because the diazonium ion that is produced, N2 plus Cl minus, that is very unstable. So temperature must be low. And if you are treating with this N2 plus Cl minus, ultimately NH2, it is the net reaction is conversion of NH2 to Cl. So this is molecule A. Then Cl and HNu is used. Now when it is light induced chlorine reagent, now aliphatic hydrogen, that will be replaced by Cl. So here you cannot replace this aromatic hydrogen. That is, if that is replaced by Cl, it means it is example of electrophilic aromatic substitution. But here that is not the case. When it is HNu, light, and some halogen you are using, now this if there is any aliphatic carbon hydrogen, that will be converted to CCl. So this is B. And finally sodium diethyl. So this is reaction, remember, if you have taken 2 molecules of this CH2Cl and also another molecule same. Now what will happen? In presence of 2 sodium, remove NaCl, there will be CC bond formation. So that is why this is the newly generated CC bond, but 2B molecules you have to take in. When you take 2B in presence of sodium diether, you are getting 1 molecule of C. Okay, so this is the major product. That means some other products may also be produced, but these will be the major. But if you are thinking that why not the chlorine which is directly attached to aromatic ring, that chlorine is not replaced, because if that is replaced, this type of compound you will get. But that is CC bond, that will be directly with the bonds of aromatic ring. But removal of haloarene halogen, that is not easy process, because cleavage of this bond is not easy. And why it is so, that we have already discussed in detail. There is some partial double bond character. So Wood's reaction, that will occur only with this haloalkane. Haloalkane, that is CH2Cl. So that is by option 3, that will be the correct option. This chlorine will be remaining intact, and this is Wood's reaction. Here starting material I having formula C3H6Cl2. Options are 1, 2, 3, 4. In presence of aqueous KOH, we are getting 2. Then 2 is treated with CH3MgBr first, which is Grignard reagent, and we always know Grignard reagent, when we use, the second step is always acidic condition hydrolysis. So H2H plus is also there. We are getting 3. Then anhydrous ZnCl2 and concentrated HCl. Finally, there is turbidity, but this information is very important, which will actually help you to answer the question. It is saying that you are not just getting turbidity, but you are getting it immediately. That means the reaction is highly facile. Okay. Now C3H6Cl2. C3H6, if you simply replace this chlorine, the formula will be C3H6, 2 more hydrogen. That means it will be 8. Now, if you consider the structure of 3-carbon alkane, that is propane, CH3, CH2, CH3. So this is actually alkane. So this C3H6Cl2, that is compound 1, that is actually alkane derivative. That is, if you replace 2 carbon hydrogen with 2 chlorine, it will be alkane derivative. Now alkane derivative, here 2 different types of carbon hydrogen there. Either you consider the terminal 2-methyl group or the middle CH2. Now, how many different types of positions possible for 2 chlorine? The 2 chlorine, they must be, they can be in 1 and 2 carbon, which you can see in option 1. It may be with same carbon, but the same carbon is the first, any of these 2 terminal methyl. Then 2 chlorine, they can be at 1 carbon and 3 carbon. This is another possibility. And the fourth possibility, 2 chlorine attached to the middle carbon. Okay. Now you have to find the which is the actual structure of compound 1. So compound 1 is any of these options, but the final information is saying it gives turbidity immediately. That means when remember how we differentiate different types of alcohol? We use Lucas reagent, and in Lucas reagent, when it is 3-degree alcohol, there is immediate turbidity formation. If it is 2 degree, it takes some time, around 5 minutes, and if it is 1 degree, the reaction is very, very slow. That means after using anhydrous ZnCl2 and concentrated HCl, which is basically the Lucas reagent, so 3 must be some alcohol. So it must be some 3-degree alcohol. Then only this type of immediate turbidity is possible with this Lucas reagent. So now you know that 3 is 3-degree alcohol. And if you know that it is 3-degree alcohol, now you have to understand what is the structure of 2. Because you are using CH3MgBr, this Grignard reagent. And when the product of Grignard reagent is 3-degree alcohol, then the starting material, it cannot be aldehyde, because from aldehyde we cannot get 3 degree alcohol. It must be ketone. So 2 must be ketone. And when if it is ketone and you are using aqueous KOH with haloalkane, that means Cl will be, haloalkane means simply we can write RCl. You are using aqueous KOH, so you will be getting ROH. But in our case, there are 2 chlorine. So 2 carbon chlorine bond will be converted to 2 carbon OH bond. But 2 is ketone. But how it is possible? So it means it must be geminal type of compound. That is, same carbon must contain 2 Cl. Then only after KOH, aqueous KOH treatment, this type of geminal alcohol will be produced. And when there is geminal alcohol, we know water molecule is removed. So ultimately you will be getting C double bond O. Both sides there are some R groups. So it is ketone. Now geminal alcohol, sorry, geminal, yes, it is geminal alcohol. 2 must be geminal alcohol. You can get only from molecule either option 2 or option 4, because 1 and 3, the 2 chlorine, they are not attached to same. So you can cancel these 2 options. Now if it is option 2, then double bond will be generated at the terminal carbon. That is, C double bond O will be generated terminal carbon. That means it will be aldehyde. But 2 is not aldehyde because 3 is 3 degree alcohol. 2 cannot be aldehyde. That means correct option will be last one. So if you think all these steps one by one, though it is not very simple, even without drawing the structures, you can reach the correct option just by applying all this logic. So here when these 2 chlorine, it will be converted to OH and OH. Then this type of mechanism will be there. Ultimately, there will both sides there will be 2 CH3. So this is acetone. That means 2 is acetone. And with acetone, if you are treating it with CHMgBr, now it will be converted to CH3 3COH, which is 3 degree alcohol structure 3. So this is the structure of one, that is option 4. First you are getting this unstable geminal alcohol, water will be removed, you are getting acetone, which is structure 2. Next CH3MgBr. So this is it will be attacking, it will be acting as nucleophile. It will attack here. First there will be formation of, that is before acidic condition hydrolysis, first there will be formation of OMgBr, but after water and hydrolysis directly the alcohol structure is given. I am just drawing the intermediate structure. This OMgBr, it will be converted to OH. So this is 3 degree alcohol molecule 3. And finally you are using Lucas reagent, gives turbidity immediately because it is 3 degree. So correct option is last one. Major product of the following reaction. In following reaction, we have a molecule which is treated with KOH. Now, whether it is alcoholic or aqueous, that is not given, but that is also not required because it is directly mentioned SN2. So this is substitution. That means Br will be substituted by OH. Okay. But the starting material, there is double bond, CC double bond, and the carbon where the leaving group is attached, that is its stereoisomer. It is already mentioned in the structure whether the CBr bond is above the plane or below the plane. And also there is another chiral center because NH2 group is also there. So this is chiral center, this is also chiral center. And you are doing SN2 reaction. So CBr bond, that will be converted to COH bond. We know when it is SN2, inversion is there. That means HO minus, which is coming from KOH, that will always attack from the back side. Now as it is attacking back side, that means the newly generated bond COH, that will be just like this. Rest of the part there is no change. So you just have to focus on this part. Rest of the part you have nothing to do. So now COH bond and CNH2 bond both are below the plane, right? So this is the structure that you will obtain. Just focus on this structure. Can you find this structure in any of these options? Because 4 options are given, you have to choose the correct option, which is basically the structure of the product. But which option is correct product? How you will understand? Now here, though the scheme is written, and after writing this molecule that you are getting from SN2, there is also some 180-degree rotation. But I will suggest you don't have to do so many things, though it is given here. But I will suggest you don't have to write the structure. Suppose if you are lacking in time, then also you can answer the question, but by simply applying a logic, which is very easy to understand. We know in SN2 inversion is there. That means CBr bond, now it will be like this. Now both OH and the existing NH2 group, both are same side, both are below the plane. But if you look at option 2, 3, 4, they are not in the same side. Either OH is above NH2 below or NH2 above OH below. So they are not in the same side. Same, it may be above the plane or below the plane, but they are not same side. This cannot be the correct. So this much information is enough to choose the correct option, which is option 1. But now if you are thinking, this is not the structure of option 1, this one. But actually, it is just the that is perspective, from which perspective you are seeing the molecule. It is true that this one you are not finding any similarity with this, but this is also one. Just what you have to do, you have to do rotation, which is 180-degree. But remember, it is not in plane 180-degree rotation, it is out of the plane. So you have to do the rotation like this. Just flip the molecule. Actually, better we use the word flip. Then what will happen? Now see this methyl also now this side. So now you can get some similarity with the option 1 structure. But again, I'm saying, even you don't have to do all these detail, draw the product structure. But this much information that now both OH, NH2, they will be same side. But in option 2, 3, 4, they are not same side. So that is why option 1 is correct. And if you can draw this structure, that is also fine. Okay, so option 1 is the correct option. For the given reaction, you have to find what is A, which is major product. Starting material, CC double bond. Actually, it is CH3CH double bond CHBr. It is alkene, but with CC double bond, there is also CBr bond. Sodium amide we are using, which is basically the source of amide ion, which is very strong base, and this type of strong base you can use for elimination of HBr. So first there will be elimination of H and Br. So if this H and Br is removed, because you cannot remove this one. This is alpha carbon with which bromine is attached, so that is what is alpha carbon. This is beta carbon, so this is the beta hydrogen, and that will be removed. So what type of structure you will be getting? CH3, C, triple bond, CH. And we know whenever there is any CC triple bond, what kind of substitution both sides, irrespective of that. If you have CC triple bond and you are using red hot iron tube 873 Kelvin, very high temperature, then this type of mechanism occurs. Both sides, there may be any group. I am not writing that. In general, if you want to see, so this type of mechanism will be. So there will be generation of new CC bond. These are the new CC bond, and all this triple bond that will be converted to double bond. And there may be any groups. But in our case, one side we have CH3 and another side we have H. So to have the maximum stable arrangement, the molecules will be arranged themselves in such a way, when hydrogen is on this side, right hand side, then CH2 will be here and H. Now we will not write H here and CH3 here, because two CH3 side by side, there will be hindrance, steric hindrance. So this will be H, this will be CH3. So in this way, what will happen? All the three CH3, they will be symmetrically distributed. So now you can understand option C will be the correct option. And this molecule is known as mesitylene. Why it is important to know the name? Suppose in the question, instead of getting the giving the structure, if it is mentioned simply mesitylene, if you know the structure and its name, then also you will be able to answer the question. Okay, and this is obviously not correct, because we have simple benzene ring, but in the starting material we have total 3 carbon, and here final product, actually 3 of these molecules will be reacting with each other. So that is why in the final product there will be total 9 carbon. 3 into 3, 9 carbon. Major product obtained from E2 elimination of 3-bromo-2-fluoropentane. In options 1, 2, 3, 4, you can see 4 different structures are there. As it is E2 elimination and starting material is 3-bromo-2-fluoropentane. Starting material is after all alkane. It is haloalkane, but it is alkane. There is no CC bond, CC double bond. And after elimination, obviously a CC double bond will be generated. So you can see in all the options there is CC double bond. But question is whether bromine will be leaving group or fluorine will be leaving group. Because if fluorine is leaving group, option 1 or 2 will be correct. And if bromine is leaving groups, then any of 3 and 4 will be the correct product, right? So first we'll draw the structure 3-bromo-2-fluoropentane. Simply you draw the pentane, which is 5 carbon. 2 position F, 3 position bromine. But bromine is always the better leaving group compared to fluorine. Now if bromine is better leaving group, this carbon is alpha, this is beta, this is beta. So bromine leaving group, but the next question is which beta hydrogen you will be removed, because if you are removing the hydrogen which is in the left hand side, then you will be getting this product, that is where fluorine is attached to the CC double bond directly. But if you are removing the right hand side beta hydrogen, now this will be the product. These two obviously not correct, because fluorine cannot be leaving group when bromine is present. Now among 3 and 4, which one will be correct? It will be option 4, because the hydrogen which is present in this case, as there is also electron withdrawing group, fluorine is present. So this beta hydrogen will be more acidic compared to the other beta hydrogen, and acidic hydrogens are always preferred for removal in elimination. So keeping 2 points in mind, one is bromine will be the leaving group, not fluorine. So this is alpha carbon, beta carbon, beta carbon. There is 2 beta hydrogen, there is 1 beta hydrogen. This will be chosen, not this one, because it is more acidic hydrogen. Keeping all these factors in mind, this will be the correct option. That means option 4 is the correct option. Compound A, which is C8H9Br, it gives pale yellow colored precipitate when warmed with alcoholic AgNO3. Oxidation of A, if it is done, it gives an acid which is B. Formula of B is given. C8H9Br, which is A, oxidation of this molecule, you are getting this one. B easily forms anhydride. That is, after formation of this acid B, it can form anhydride easily if you are heating. From these 3 information, you have to find the structure of A. Now, as it is saying B is forming anhydride, that means there must be 2 CO2H group, and 2 CO2H group, they must be close to each other. Then only anhydride formation, that is water molecule removal, that is possible, and anhydride formation is possible. Now whenever you have this type of structure, and in the options also you can see all are, that is structure of molecule A. Now all are aromatic ring, and if you have still any doubt, you can also take the help of the formula, which is for degree of unsaturation, so that you can understand how many double bonds or rings are there. So from this formula you can apply it. 2 carbon means number of carbon, which is 2 into 8 plus 2. There is no nitrogen. There is hydrogen, how many? 9. So it will be minus 9, and X is halogen, 1 halogen. So it will be minus 1 divided by 2. So basically it is 2 into 8, 16, 16 plus 2, 18, then minus 9, minus 1, then 2, so it is 4. So it is matching with aromatic ring, because in aromatic ring you have 3 double bonds and 1 ring which is matching with this value of degree of unsaturation. But among these, which one will be the structure? Now as both the CO2H group must be close to each other, that means the two groups must be ortho to each other. Only you can find two groups ortho to each other in option 3. So see, when it is option 3, you are doing oxidation. Basically you are getting 2 CO2H, both will be converted to CO2H, they are ortho to each other. So that is why this type of water molecule removal is possible, and it is phthalic acid structure. And the first information, you are getting pale yellow precipitate, which is basically the precipitate AgBr, that will be formed from Ag plus ion and this Br, and there will be benzylic carbocation like this. So actually this information is most important, that it is saying B can form anhydride easily, and as there are total 4 oxygen, that means 2 CO2H group will be there, then only 4 oxygen you can match. And the first information, that it is when warming with alcoholic HNO3, there is a pale yellow color. So it proves that there must be aliphatic carbon bromine bond. That is, bromine is not directly attached to aromatic ring, because if this is the structure of A, you cannot get AgBr precipitate, yellow precipitate. That is not possible, because there is partial double bond character present. But if Br is attached to some aliphatic carbon, then it is possible. But problem with option 2 and 4 is that it is meta position, this is para position. So that is why anhydride formation not possible. But in 3, it is ortho, that is why this will be the correct option. Okay. So we have discussed in today's class only problems. I think it will be helpful for you. We are ending the session here. Thank you for listening.